So if you wanted to run WordPress in a highly available way, this is what it would look like. And you can see there's an awful lot of things going on there. We've got servers, we've got databases, we've got load balancers. We've got all these other things that we need to manage, we need to operate, we need to think about. That's an awful lot of work for people to be doing just to run WordPress. And this is what serverless aims to help you do. It aims to help you deal with this undifferentiated heavy lifting. The things that come with applications that actually don't add any value to the people using your systems. Because how well you can run your server or operate a Kubernetes cluster isn't going to make a difference to the users you are working with. It's the features you can add to your application, the differentiators that differentiate you from your competition. So where do we start? Hopefully I've made a pretty convincing case there about why you might not want to use server-based workloads. And a lot of these ideas are the same. You might be using containers running on top of servers. You've still got servers to manage under there somewhere. So where do we start if we want to be truly serverless? Well, at AWS, that is with AWS Lambda. So another quick show of hands, who's heard of or used AWS Lambda? Many hands, excellent. Let's see. So fundamentally, AWS is event-driven compute. That is Lambda's superpower. It's completely reactive to things that are happening within your system. So with Lambda, you can define an event source. That could be an API request. That could be an event that happens somewhere else in your system. That could be a message on a queue. And that will then invoke your Lambda function. And you can deploy code to Lambda using a whole range of programming languages natively, what we call a managed runtime, .NET being one of them, but also Node, Python, Java, Go, Ruby. And you can also bring a custom runtime, so you can actually deploy applications on Lambda using any programming language, providing you can interact with the actual runtime itself. And this is where Lambda gets really powerful. Like I say, it's completely event-driven. When there's no events for Lambda to react to, your code is costing you nothing. It will scale to zero. And there's a few different ways you can invoke a Lambda function, and we'll just touch on all three of these just briefly. So the first is what's called a synchronous invoke. And a synchronous invoke where something's going to invoke your Lambda function and it's going to sit and wait for a response. So that's how Lambda will work with things like API Gateway, which is AWS's serverless API Gateway service. So a request will come into your API, an API Gateway will invoke your Lambda function, and it will sit there and wait to the point in which your Lambda's finished running. Your Lambda will return a response back to API Gateway that will then come back to your caller. If your Lambda function was to fail for any reason, you then get a 500 on your API. It's kind of the easiest and the most common that we see, at least when people get started with Lambda. The second invocation model is what's called an asynchronous invoke. And that's where you call your Lambda function and your caller can just go off and carry on doing other work. How this actually works under the hood is if you send an asynchronous invoke to Lambda, Lambda will place that in a queue internally to the service itself. You don't need to worry about this queue. And then periodically Lambda will just pull things off this queue and invoke your actual function code. That time on queue is typically 2, 3, 4 milliseconds. It can get bigger and you can monitor that natively in AWS. And that's how typical event-driven applications work. You might have an event happen in your system that gets published to a service like Amazon Simple Notification Service. That will then invoke your Lambda function. SNS will carry on doing other things and not wait for a response. It doesn't care. Once the service can deliver that message, it'll carry on doing other things. And yeah.
Are they guaranteed to be processed in the same order as they were submitted?
So that does depend. So talking about SNS specifically, there's two options you have there. You've got standard SNS, which is absolutely no guarantees about ordering, and then you've got first in, first out SNS, which is guarantees you're ordering, but you get a lot less throughput, is the trade-off you kind of make there.
What about if it was S3, that was your trigger?
No.
No guarantee?
No guarantees.
So if you had 15 changes to a file, then, object, then potentially the final one to execute might not be the final.
Yeah, that's something you need to manage in your application itself in the Lambda function. Now you could get around that. So if you use something like Amazon SQS, which is the simple queue service, you could have a first in, first out queue. And before you write to S3, you write to your first in, first out queue, and you have a Lambda function that pulls on the FIFO queue, and then you interact with S3. So then you're not guaranteeing it at an S3 level, but you guarantee it at the queue level the place before that. But yeah, S3 won't give any guarantees. And the final invocation method is what's called the poll-based invocation method. And this is how Lambda works with things like SQS, and this is actually what I think is one of the most valuable execution models, because this is where Lambda will actually poll these services on your behalf. So if you imagine you were working with a queue in your application, and you have to manage pulling the messages off the queue. How many messages do you want to pull off the queue? Do you want to wait until you have a certain number of messages? And once you process the message, you've then got to delete that message off the queue once you've processed it, right? Lambda will handle all that on your behalf. So if you set a queue as a source for a Lambda function, Lambda will do all that for you. You can set up how many messages you want in a batch, how long you want to wait to give that batch time to fill up. And once your Lambda function's finished processing, it will then delete the message from that queue as well, provided there's no errors. And this is how it works with things like SQS, for Kafka, so you can use Kafka as a source for Lambda, DynamoDB streams, and Kinesis. And that's a really, really useful execution model. So the next thing that's really good to understand with Lambda is how Lambda actually works behind the scenes, because if you are familiar with things like Azure and Azure Functions, Lambda is slightly different to how Azure Functions work. So when you invoke a Lambda function, regardless how you invoke it, regardless which of the three methods you use, it will always end up with what we call the invoke service. And what the invoke service is going to do is it's going to look for what we call an execution environment. And that's a completely isolated environment that has the prerequisites for the specific version of your Lambda function and the code within that. If the invoke service can't find an existing execution environment, it'll go off and create one. So it'll create this completely isolated container, it will download your function code, it will load up the runtime, and then it will actually execute your code. So that first bit, that initialization phase, is what you'll know as a cold start. That's what we call cold starts on Lambda, where these things have got to happen. And that can range based on which programming your language you're using, from 400, 500 milliseconds with things like Node and Python, right up to 6 and 7 seconds with runtimes like Java. So it can vary dramatically based on what you're doing in that initialization phase and also what runtime you're using. With that initialization phase, anything that happens there is completely free. So when I said Lambda's got a charge per millisecond, you don't get charged for this initialization phase. So the execution environment is now available, the request gets passed to that execution environment. Each execution environment can only process one request at any one time. So if you receive 2 requests into your API at exactly the same time, you're likely to get 2 separate environments, 2 separate cold starts. Now once these execution environments are available, they do hang around for a little while. They do stay active to make things more efficient, so we're not loading these execution environments every time. Now there's no SLA on that, so you need to consider really that Lambda's completely stateless. You can't store state within Lambda.
Although you need to consider that it's not entirely stateless for debugging.
Yeah, that's fair. Yeah, absolutely. So yeah, typically, it can vary how long they hang around for. If you've got no activity on your Lambda function at all, it will shut itself down. Periodically, even if you've got a lot of load, they will get turned off periodically and recycled periodically. But yeah, from a debug perspective, you need to consider the fact that you might have multiple invokes in the same environment. And these, like I said, these execution environments are completely isolated. And I think this is one of the really valuable features of Lambda, in that if you say, I need to give my function 512 megabytes of memory, you can guarantee that every single request that hits Lambda will have its own guaranteed 512 megabytes of memory. Unless, of course, you're reusing an execution environment and you've done some really crazy memory things and you've used all that memory up. But each individual invoke will get its own container of 512 megabytes of memory. So it's a really valuable thing with Lambda. One last Lambda specific thing is around how networking works in Lambda. So if you're working with serverless applications and you need to connect to non-serverless resources, typically you're going to need to interact with a network of some kind. So Lambda functions will always run within a network owned by the Lambda service. So you can't run a Lambda function within a network you own. It's just not possible. What you can do, however, is you can attach a Lambda function to your network. So when you deploy the Lambda function, you can specify a subnet to attach that to, and that will then set up this NAT gateway between the Lambda service network and your own managed network. A couple of reasons why you might want to do that. The first, as I said, you might need to connect to a SQL database, maybe an API that's still running on an actual physical server. You might need to connect to these non-serverless resources that are still running within a network. The other thing you can do if you configure this is all of the network traffic that leaves your Lambda function will now run over this connection. So if you have any requirements around things like firewalls or checking all the traffic that's flowing out of your network, you can do that with Lambda by attaching it to a VPC. And that's something I see quite often with customers, is that although you can run Lambda completely independently on its own, actually connecting it to the network allows you to be a bit more smart with how you do security and how you monitor the network traffic. Okay, so what can we actually configure on a Lambda function? What different knobs can we tweak, so to speak? So there's a couple of options here of things that we can deploy. So the first one at the top, obviously you can see we can define a runtime, and we've already said you can do things like .NET, Java, Node, Python, Go, all natively supported within Lambda. You can configure the memory, and from a performance perspective, that's actually the only thing you can change. You can configure the amount of memory allocated to your function. As you scale up your memory, you scale up the number of virtual CPUs, and you scale up the amount of network throughput that you get on your function. And the charge of Lambda is based on the amount of memory you allocate, so the per millisecond cost changes based on that allocation. And this is again something that's really interesting, that if you allocate a higher memory to your Lambda function, that's going to cost you more per millisecond, but it might actually be cheaper overall if your code runs in a tenth of the time. And there's a tool that we've got later in this talk that actually helps you analyse that and work with that and understand what's the best configuration for your application. We then define a handler. So this handler will change based on what runtime is you're using. So I'm using .NET, so this gets a bit more complicated. You need to define the name of the assembly that you're working with, and then the namespace and the class, which is that hello lambda.function, and then the method that you want to invoke on that class, which is function handler. If you're a Python or a Node developer, this is a lot more simple because your handler is just index.js or index.py. You just specify the file you want to invoke. And then there's a few other bits in there. We've got the name of the function we want to deploy, the architecture. So Lambda supports both x86 and ARM-based architectures. But the main one, really, from like a performance perspective, is the memory. The memory is the main thing you're going to want to tweak as you start to work with your application. Okay, some .NET specific stuff now, and we're going to look at how you can both take an existing .NET application and lift and shift that to run on Lambda, and then we'll also look at how you can build what we call single purpose Lambda functions, functions that do a very specific single job. So to start with taking an existing API, so if you were to build a brand new API with .NET today, your API looks something like this, and Microsoft have done a lot of work on simplifying the model of defining APIs. So this is what's called a minimal API in .NET. So you can see we've mapped two routes on our API here. We've got a get route for hello that will return the word world, and then we've got a post route again on the same hello route. So this is about as simple as you can get for defining an API with .NET. I've used this example because hopefully it'll make sense to non-.NET folks as well. Now if you wanted to take this exact same application and run this on Lambda, we would add one single line of code, which is that line of code there. So there's a package that you can add to your application which will enable you to add this line of code, which will set this API up ready to run on Lambda. what this is actually going to do behind the scenes is it's going to configure a handler so that the request that comes in from API Gateway into Lambda, it will translate that to a format that your actual API can understand, process that through the ASP.NET middleware pipeline. The response that comes back will then be translated back to something for API Gateway, which will then go back out to your caller. If you're not using minimal APIs with .NET, it's almost as simple. You just need to add an additional class to your project, and you can configure a lot of this same lift and shift functionality, if you will. So it's really easy if you've got existing ASP.NET applications, providing they are running .NET Core 3.1 or .NET 6, to take them, lift and shift them onto Lambda. So why would you want to do that? Why would you want to take this existing application and run it on Lambda? Well, the first good reason to do that is that it's a really fast way to get started. If you've got an existing application, you can just pick that up, send that into Lambda, and you've got all these benefits of scale to zero if it's not being used. If it is being used, it will scale almost infinitely. It's a really, really quick way to get started, starting to work with this serverless paradigm and this serverless way of thinking. It also brings an awful lot of familiarity to developers, because .NET developers are still working within a stack and with a way of building applications that they are familiar with. That line of code that I added, if I tried to run that same API on my machine or in a container, that same API would work in both places, both in the container, on my machine, and also in Lambda. The library's context of where it understands where it's running. So that's two reasons why you might want to do that. There are a couple of reasons why you wouldn't want to do that, of course. The first is performance. So when we talked about how the execution environments worked, and we mentioned the cold starts, a cold start will typically take longer if you're running an entire API on Lambda, because Lambda needs to download the code, load up the runtime, and then it actually also needs to run the startup phase of your API and get that listener running. So you will have a performance impact. Typically for a .NET API on Lambda, you're looking at about a 1.1 second cold start, typically. So that's one reason not to do it. And the other reason not to do it is around what we call least privilege security at AWS. So when you're building Lambda functions, typically you should think about what are the least amount of permissions I can give to this Lambda function to allow it to do its job. Now, if you're running an entire API on Lambda, you need to give that Lambda function permissions to do everything that API might possibly need to do. So running that entire API means that you can't get as fine-grained with your permissions as you might want to. Now, of course, that same concept applies if you're running a server-based application, because in a server-based application, you need to give that server permissions to do everything that it might want to do. And you can also think about with the memory allocation. Remember, Lambda is priced based on the memory that you assign to it. If you had an API with, let's say, 4 endpoints, one of which needed a gigabyte of memory to do its work, the other 3 endpoints needed 128 meg. You need to give your Lambda function a gigabyte for every endpoint. So being able to get more specific and get really granular with these both security and memory configurations can be really valuable as you start to build out Lambda functions. So this is a perfectly valid way of using Lambda. And there's ways to do this for all of the runtimes. So if you're a Java developer, you can run Spring Boot on Lambda. If you're a Node developer, you can run Express on Lambda. If you're a Python developer, you can use whatever the web framework for Python is. If anybody knows, then that one.
Django,
I think it is Django. I think Django you can run on Lambda. Okay, so there's reasons to do that, and there's reasons not to do that. So what do we do with our applications if we don't want to run entire APIs on Lambda? How do we build these single-purpose Lambda functions that have got both really specific permissions but also really specific memory configurations? And that's where we get into what we would call single-purpose Lambda functions. So to keep with kind of the same example, we're going to stay with an API, and this is typically what an API would look like on AWS if you were building a completely serverless API. You have API Gateway acting as your routing layer, and you have that routing out to a separate Lambda function based on the request or the method that you're running. And each of these Lambda functions now could have their own individual configuration. Our get endpoint could have permissions to only read from our database, and our post endpoint might only need permissions to write to our database. And they're likely to need different memory configurations if you're getting, you're posting, reading and writing. So what does this actually look like? This is what a .NET Lambda function can look like. So there's quite a few different ways of defining a Lambda function in .NET, and that's developed as Microsoft have developed the .NET language. I've tried to use an example here that will be familiar to, again, non-.NET people in the room. So typically what you've got two components, two parts to a Lambda function. You've got the handler itself, the actual application code that you want to run for every single request, and you've got code that you want to run as part of that initialization phase. There we go. So anything that can be shared or reused from request to request, you want to do that work and define that outside of the handler itself. So you can see outside of our handler method there, we're both loading a variable from the environment, and we're also initializing an SDK, an AWS SDK. And the reason you're doing that is that then that only needs to happen once per execution environment.
And that's where your bugs can sneak in across runs.
Multiple invokes, yeah, absolutely. So if I was to put a counter in that initialization phase, and I was to hit the same Lambda function, say 10 times once a second, that counter would obviously increment 1, 2, 3, 4, 5, 6. If I was to hit it twice at the exact same time, I'd probably get 2 zeros back or 2 ones back. And yeah, that's where things can start to sneak in. If you're setting like static variables or things like that, that's where things can get a little bit tricky. So that's your initialization phase. Like I said, any work you can do outside of the handler, do it there, both because it gets reused and also you don't get charged for that work as well. So if you need to initialize a database connection, for example, do that in your handler, so you get a slightly slower cold start, but then everything's ready to go once you're receiving that request. And as we'll see in a few slides, cold starts actually don't affect as many function calls as you might think. The second part you've got to a Lambda function is the handler itself. This is the bit of code that's going to run for every single request that hits your function. So you see what we're doing here is we've got a request coming in from API Gateway. We're doing some work to we're not really doing anything actually, we're just describing a table from DynamoDB and returning a dictionary as part of the body. So we're not really doing an awful lot of work here, but this is where you would define your actual business logic, your actual application code in the handler itself. And again, the important thing to remember here is anything you can initialize outside of your handler, do it there. And then reuse that from invoke to invoke. That's probably the most common thing I see people doing with Lambda that isn't as optimal as it could be. It's just initializing things in the wrong place. And with .NET, and both .NET and Java, most runtimes actually, most runtimes that are more object oriented at least, AWS have a whole range of packages that have these objects that are ready built for the different event sources that you might want to use with Lambda. So you see we're using API Gateway in this top example here, and we've got an object there for an API Gateway proxy request. So the actual payload that gets passed into Lambda is just JSON. It's just a JSON string. And what the .NET runtime does on your behalf is it actually serialize and deserialize that JSON into an object for you. So we can just specify we want an API Gateway proxy request. The runtime behind the scenes will take that JSON string and transform that. We're then working with objects that are familiar, that we know have all the properties. We get IntelliSense and all that good stuff in whatever IDE we're using. And the same applies on the way back out. The response, Lambda's expected in JSON. So we can define an API Gateway proxy response object. That's just what we return. We're returning a strongly typed object, and the runtime will manage that serialization back to a string itself. And you can see in the second example there, we've got a slightly different event. We've got an SQS event. So if you're sourcing your Lambda with SQS, you can use that as well. If you just go onto, if you're a .NET developer, go onto NuGet and search for Amazon.lambda, you see all of the different event sources that are available. So you can also use dependency injection with Lambda. So if you are a .NET developer, dependency injection is probably something that's quite common, quite familiar. It's kind of the typical way of building .NET applications, is quite heavily using dependency injection. So what we've got on the left there is your typical startup class for a .NET API. Then all we're doing in that startup class on the left is we're just configuring a Amazon DynamoDB client. We're setting up our SDK, and we're doing that as part of our API startup. If we were doing that on Lambda, we just need to be a bit more explicit. We take some of the things that the runtime hides away from us, the ASP.NET runtime, and bring that to the forefront. So what we're doing is manually creating our dependency injection container. We're still adding the Amazon DynamoDB client, and then we're just building that. So what we're doing is bringing some of this logic to the forefront that the .NET runtime hides away from us. So that's how you can do. You can configure your startup class or your startup logic, and a lot of that is lift and shift. So you could take your existing startup class from your ASP.NET application, move that into something Lambda specific, and then use that in your function itself. So if we were then using that in our function, again, we've got a .NET function on the right hand side there. As part of the constructor of that function, we're just initializing that startup logic. We're just saying init the startup, and then we can pull anything from the dependency injection container that we need. So again, you can still use things like dependency injection with Lambda, you just need to be a bit more explicit. And of course, there's a cost to using dependency injection in whatever runtime you're using, because you need to set up that container, you need to actually initialize everything. So if you're doing really simple things in Lambda, or you're building truly single purpose functions, it can actually be beneficial just to get rid of the dependency injection completely and do things manually. So there is another package that AWS have released for .NET Lambda functions, and that's called the Lambda Annotations Framework. And what the Annotations Framework does is it aims to hide away some of this complexity and some of this boilerplate code that you might need when you're working with Lambda and APIs specifically. So if you were writing a function to do add two numbers, x and y, and let's say x and y are provided as part of paths on the root of your API. On the left is what that will typically look like if written in .NET with Lambda. So you see we're reading our path parameters, we're parsing out x and we're parsing out y, and we're checking that it's a valid integer, and then we're actually doing x plus y right down at the bottom, third line from the bottom. It is there. So the package that AWS have created is got the annotations framework, allows you to move more to a model like what's written on the right. So you can use attributes on your methods to say this method is going to be a Lambda function, and this Lambda function is going to be sourced by an API. That API is going to be a GET request, and it's going to have these parameters. And then our Lambda function gets really simple. It's just our business logic. It's x plus y. Nice and easy. And this uses a feature of .NET called source generated serialization. So at the point in which I'm talking nonsense there. My brain's just gone back. Anyway, when you compile the actual application, .NET will generate the code required to do this behind the scenes. So if you were to compile this and then decompile it, you would get something like what's on the left. We're just hiding that complexity away from you and adding that boilerplate code at compile time. And again, you can also do that with dependency injection. So you can have a startup class in your .NET code base, and you can just annotate that startup class with a Lambda startup attribute. And again, at compile time, all of the configuration, all of that complexity will be generated. When it actually comes to your Lambda function itself, you're just saying, I want to inject this iCalculator service, and I want to inject that from my dependency injection container. Okay, so what tooling is there available if you want to start building Lambda functions on AWS? And we'll start with some .NET stuff specifically, and then we'll move into more generic tooling that is applicable whatever language you're programming. So AWS has an extension to the .NET CLI, which actually allows you to both get started with new projects, but also deploy things once you've got started. So when you've installed a set of templates to the .NET CLI, you can just run .NET new and then pass in a template. That might be lambda.empty function, and that will give you a pre-built project with both a Lambda function and the tests required for you to test that Lambda function. And we'll come on to tests in just a minute. So that's one side of the equation. You can create new projects really easily from a set of predefined templates that are available. Once you've written all your application code and you're ready to deploy that now, you can also run a CLI command to deploy your application. You can run .NET Lambda deploy function. That will then take you through a little wizard, store a config file locally, and that will actually then deploy your application to AWS. And once you've deployed it, you can then invoke it as well. You can invoke your Lambda function in the cloud and pass in a payload that you want to test with. And we also have tooling built into all of the major IDEs that you might be using when you're using .NET. So Visual Studio and Rider are probably the two most familiar to .NET developers, but we also have a toolkit for Visual Studio Code, which allows you to really easily do things and interact with AWS resources right from within your IDE. So we'll talk about Visual Studio just very briefly. So if you are using Visual Studio as a .NET developer, you can do a whole range of different things when it comes to serverless applications. So if you're creating a brand new application, you can go File, New Project within Visual Studio, and as part of the templates that are available, you will get a whole list of Lambda specific templates that you can use as a base to work from. When it comes to testing your application, you can actually start your debugger locally within Visual Studio. This would work in Visual Studio Code and Rider as well. And it'll actually launch a web browser on your machine that you can then use to actually invoke your Lambda function. You can pass requests into your Lambda function, define a payload in the big text box, and then you can step through that within Visual Studio itself. That development experience that we're all used to, where you run it locally, step through your code, and actually see what is happening within your application. You can also deploy from within Visual Studio with any of the IDEs. If you've got a Lambda project within Visual Studio, you can right click, you can say publish to AWS Lambda, and that will then take you through a wizard within your IDE that will actually then deploy that function to Lambda. It will package it up, it will create all the resources necessary, and it will deploy that actually into the cloud, from which you can then invoke the Lambda function actually running in the cloud. So once you've got the toolkit installed, you see you've got the window on the left hand side there, you can see more than just your serverless resources. You can interact with more than just your serverless resources, but you can actually invoke Lambda functions from within your IDE, hit and get the response back into your IDE that actually came from the function running in the cloud. So that's enough of the .NET specific tooling. Let's talk more generally now about ways you can build serverless applications on AWS outside of .NET. And we'll start with testing, because testing is one of the most common things that I speak to people about, is like, how do I test these applications? Because typically serverless applications are lots of these small little pieces of compute that are all joined together by various different services in between, and queues and event buses, and it actually gets quite hard to test your application as a whole. And the guidance we typically give is that you want to unit test locally. So test your business logic on your machine, mock out any external integrations. If you need to talk to a queue or talk to a database, mock that out, do that locally. Once you actually want to test anything else, test that actually in the cloud. Get your function running in the cloud and test it there. So there are services you can use to like emulate AWS services locally, and they're great if you've got no internet connection, you're on a plane, something like that. But a lot of these emulators don't directly reflect the actual service that's running in AWS itself, because of course some of these emulators aren't managed by AWS, so they can't be quite as feature complete. And actually you're also not testing things like permissions. something that got quite wrong. Remember we said that we want to give Lambda functions really specific permissions to do the work that they need to do. If you're testing that locally, you're not testing these permissions, you're only testing your function. So mock your integrations locally, unit test locally, and get it in the cloud as quickly as possible, and test it against cloud resources.
Do AWS give you any sort of mocking objects or mocking services? Do they provide anything? Because it's often something you want to be able to work with locally, pull something off. Is there anything like that that AWS provide that you can actually develop?
So there's nothing AWS provided. There's an open source project called Local Stack, which is typically what people emulating AWS services would use.
It's a little bit open source.
Okay, a little bit open source.
If you want to fully emulate things, you need to pay money and use proprietary stuff.
Yeah. So yeah, there's nothing AWS specific. It's something that we are looking at, but
buy out OpenStack.
possibly.
It's something that would be really handy, actually. I think that.
Yeah.
To be able to do that.
Yeah. Yeah. I mean, for development purposes, so things like Lambda specifically, you get 1 million invokes for free every month, from like a free tier perspective. And most of the serverless services have got similar levels where if you're purely just developing, the chances of hitting them and then limits are impossible. Of course, you can spend money doing this, but
if you create some sort of feedback loop that's
the most common one is you have an event, you have a Lambda function that triggers off an S3 event, and then writes something back to S3, and then triggers the Lambda function again, and everything gets stuck in this crazy little loop rift.
It's not a loop, it's a web. It out, assumes that no universe.
Yeah. But no, to answer your question, there's no emulators specifically provided by AWS. There are open source projects. And yeah, again, like I said, the reasoning being that even if you were to have an emulator locally,
it's not going to be quite the same.
It's not quite the same.
Yeah.
So there's a really cool project actually by, I don't know if any of you have heard of Thundra, the observability people called Thundra. So they've got a tool called Murloc, which is in their labs GitHub at the minute. But what Murloc will actually do is it'll intercept the request that's coming into the cloud, route that to your local IDE using WebSockets, and you can step through the code locally, but it will actually assume the role of the function running in the cloud. So you get that local dev experience with a request that's actually coming into AWS, and you assume the role and everything. So there is both internal and external tools that are being looked at, but at the minute. This is typically how you would define a function ready to be mocked or to be tested. So you see we've got two constructors on this function here. We've got both a public constructor, and that public constructor is needed by the Lambda service. It requires there be a parameterless constructor that it can use to initialize the object that's used for your function. We've then got this internal constructor as well, which is actually taking a DynamoDB client as one of the parameters. This is what enables the unit test, because then you can use whatever mocking library it might be, whatever mocking library it might be in your runtime of choice, to actually mock out this SDK call, pass in your mock, and then you can use that instead of actually needing to worry about interacting with DynamoDB while you're running things locally. And of course, when I'm saying unit test locally and integration test in the cloud, there's no reason you couldn't run a test locally from your machine actually against DynamoDB in the cloud. Using this same method, you could actually just pass in an actual instance of the DynamoDB SDK. Maybe you've configured that with some custom credentials for your development environment. So you can still test against cloud resources, debug locally against cloud resources, but when you're testing how your code works with other things, DynamoDB, SQS, event buses, do that against actual cloud resources, not against emulated or local things. So there's a few frameworks available that can really help build serverless applications. So some of the tooling I've talked about already, so the .NET CLI and the integrations built into Visual Studio, they're great for getting started, because you can do file, new project, start a new project, right click and deploy from within your IDE. But of course, I don't imagine many of us are actually deploying our production applications from a right click and deploy from within an IDE, at least I hope we're not in 2023, but here we are. So there's a few tools that are available for doing this. There's a couple provided by AWS, and then obviously there's some open source options as well. So the two that I'm going to talk about today are the AWS options, of course, both AWS SAM and the AWS Cloud Development Kit, but you can also build serverless applications both with Terraform and with a third-party product called the serverless framework. Of course, the benefits of the Terraform and the serverless framework being they're both more cloud agnostic, whereas SAM and CDK are very AWS specific. So let's start with AWS SAM, or the serverless application model. Now, aside from having a really cute mascot, the serverless application model is an open source framework that helps you define serverless applications. There's two parts to SAM. So the first part is a set of extensions that run on top of CloudFormation. So if you're not familiar with CloudFormation, CloudFormation is the AWS infrastructure as code service. So you can define your AWS resources in YAML or JSON and then deploy them repeatedly with AWS. So what SAM does at that side is it adds some abstractions on top of CloudFormation to make it easier to run serverless applications. The other side to SAM is the SAM CLI, an actual terminal that you can use to both initialize, package, and deploy and test your serverless applications. So let's start with the abstractions on top of CloudFormation. So this is how you would define a Lambda function using CloudFormation. And there's a couple of really useful abstractions that SAM adds here. So if you're using a compiled language like .NET or Java, you can simply specify the path to the location of your code. In .NET, that would be the path to the project file. If you're using Java, that would be like the path to the pom.xml if you're using Maven. When you actually build this application, SAM will compile the application on your behalf and do all that for you. If you're using CloudFormation natively, you need to compile the application and then deploy it with CloudFormation. The second useful thing that SAM adds is this idea of policies. So you can see on line 10 there, we've got this policy section, and we've got DynamoDB read policy. So SAM gives you a set of pre-built policy templates to do the kind of common things you might want to do with a serverless application. So if you dive into like identity and access management on AWS, you can get as granular at every single individual API call that you might want to make. And that can actually get quite difficult to remember. You know, I need to read from a DynamoDB table, a database, what exact API actions do I need to give to my function for it to be able to do that? What SAM allows you to do is to simply say, I want a policy, a DynamoDB read policy, and at the point when you package up this application, all of the requisite permissions will be added to your Lambda function without you needing to remember the individual actions. There's a pre-built policies for things like DynamoDB for databases, SQS for queuing, S3 for object storage. And this is a really easy way to, like I say, you don't need to remember the exact actions that you need. And the other really useful thing, especially when you're building APIs, is that events section that you can see there. So if I'm building a Lambda function that I want to be sat behind an API, all I need to do is define in my event section that I want an event source of type API. I define the method and the path. And SAM will handle the configuration of that API. It will create an API gateway on my behalf. It will set up the integrations between API gateway and Lambda. It will map all of them permissions and all that resources for you. It will do all that without you needing to do anything. If I have 4 Lambda functions in this same resource, all with events, it will create one API and set up all them integrations on my behalf. When it actually comes to using the CLI side of SAM, again, there's a few different commands that you'd want to use in the CLI. So we've got the SAM init command, which allows you to create a brand new project, and I'll show you some of this if we have time for a quick demo. You can both compile and deploy your application using the SAM CLI. And then actually the last 2 commands there are some of the most useful. So SAM local allows you to invoke your Lambda function locally on your machine, and you can do that using the mocks and the things we've just talked about with testing. You can actually run the Lambda function locally as if it's running in the cloud.
Is that running against cloud resources, or is that with mocked resources?
That would depend how you handle that in your application code.
Right.
So you could say in your application code, if environment variable is dev or is local, then use mock resources, else use, but that would be up to you to handle as a developer. And then you've also got the SAM sync command. So if you run the SAM sync command, what SAM will actually do is it'll watch your local file system, and every time you make a change to your application code locally, it will then trigger a redeployment of that resource to the cloud. So that allows you to get into a really nice cycle where you can be working on your code locally, run your unit tests, hit save, that will get deployed to the cloud, run your integration tests, and you might be doing all of this locally. So SAM sync's really fun. Again, I'll show some of this in action. I'm going to skip past that because we'll have to look at that. So the other way, the AWS native way at least, that you can define serverless applications is with the AWS Cloud Development Kit, or the AWS CDK. Now the CDK, again, uses CloudFormation behind the scenes to actually deploy your application. But what the CDK allows you to do is define your resources using a programming language that you're familiar with. So you can define resources in .NET, you can define resources in Node, or Python, or Java. So it allows developers to use a language that they're familiar with to start to build out their application. So you can get to a world where both your application itself and the resources it needs are all defined in the same language. And this is what a CDK, .NET project might look like. So you can see just about that the first resource we're defining there at the top is an S3 bucket. So we create an S3 bucket, again this is all just .NET code, and then underneath we're defining a Lambda function. Again, CDK has both the resources you define in your application code, but also a CLI, so you can run CDK deploy. That will take your application code, depending on how you defined it, translate that down to CloudFormation, and then deploy that using CloudFormation. And the two work really well together. You could use SAM for maybe using SAM sync and using that really quick feedback loop as a developer, but when it actually comes to deploying into production, you might want to use the CDK. Or you might want to use the CDK if you're doing both serverless and non-serverless resources in the same microservice or the same project. Okay, so a little bit more .NET specific stuff now around best practices and performance optimizations. The first thing is a product called AWS Lambda Power Tuning, and actually I've just lied to you all because this isn't .NET specific at all. So AWS Lambda Power Tuning is a service you can deploy into your AWS accounts, and you can tell Power Tuning to run against the specific Lambda function, and you can pass in a sample payload. And what Power Tuning will actually do is it will run your Lambda function over and over again using a set of different memory configurations. And then it'll give you a really nice looking graph that you can almost see down at the bottom there that will give you both the best price and the best performance and the optimal combination of both. And this can actually give you some really interesting results. So the sweet spot for .NET seems to be about 1 GB of memory, which is, the lowest you can do is 128 meg and the highest is 10 gig. And the sweet spot seems to be about 1 gig for most .NET applications. And it can be really interesting if you're using Lambda today, or you're thinking about using Lambda, that initial allocation of memory can be, it's almost a guess, at least initially, until you work out how your function's going to run. You can use Power Tuning to pass in a sample payload and actually get the exact specific memory that's either going to really, really over-index on performance. You might not care about cost and make it as fast as possible, or you might want to be really cost efficient and not care so much about performance. Typically, actually, you find the cheapest cost is also the fast performance, interestingly. Again, so this is .NET specific code, but the examples here apply for any programming language, and it's kind of what I was talking about before around where you initialize things. So anything that you can reuse from invoke to invoke, do that outside of the handler itself. Do that in your constructor or
Are there any restrictions on execution time?
Yes.
for your init phase. 10 seconds. So what Lambda will do is you get an initial set of 10 seconds
Yeah.
that you get for free.
Yeah.
If your initialization doesn't finish in that 10 seconds, it'll start again. And that you get more time, but then you get charged for it.
So your function itself, when it's actually doing its job.
Oh, sorry, 15 minutes.
Right.
Sorry.
And is that different for synchronous and
30 seconds when it's, well, it's API gateways and it's got a 30-second limit.
Yeah, so your init phase, the initialization phase, you've got an initial 10 seconds, which is completely, that's free.
Yeah.
That's purely the init. For your actual handler, yeah, you can do anything from a second to 15 minutes. Quite rightly pointed out that if you're using API gateway, that's limited to 30 seconds. But that's an API gateway limitation, not a Lambda limitation. If you are doing anything that you need to go longer than 15 minutes, there's another AWS service called step functions, which you can do to orchestrate multiple runs of a Lambda function. Or actually, if you need something longer than 15 minutes, that can typically be something that isn't a good use case for Lambda, right? If you've got a really long running batch job that you can't chunk up into individual little chunks of work, that might be a reason not to use Lambda if you've got a really long running job.
Yeah, we've definitely come across where the first batch we want to run is going to be a long one, but everything after that's just the cream. So, we either have to do it locally, that first batch.
It depends if it's 50,000 individual tasks in that batch, then it can be split. So that Lambda could potentially do it all at once, which works quite nicely.
Yeah, there's a new feature, so step functions.
And you can check in with those as they're working as well, just to see what the status of each.
You can configure it to do whatever you need it to do. So I've had batch jobs that were an hour-long job before, but once they've been correctly switched to Lambda, they're 7 seconds. They just run 3,000 or so instances at the same time.
Yeah. I had a question last week actually about, let's say the use case was they had a CSV file, a massive CSV file they wanted to process with Lambda. And of course, initially you might just chuck that as CSV file in S3, trigger a Lambda function from that S3 event, and then process your CSV file, right? But what you could actually do is from that S3 event trigger a step function, which is just a workflow engine if you're not familiar with step functions. The first step of your step function will be to chunk that CSV file up into well-defined sets of 10, for example. And then you parallelly, I can't never say that word, but parallelly execute however many thousand instances of Lambda at the same time. So yeah, there's different ways you can configure it, it's how you handle that. As a default, you can get, when we talked about the execution environments, you can get 1,000 concurrent execution environments. So that's 1,000 concurrent jobs running at once, if you will, but that's a soft limit that can be increased, and it can be increased considerably. I guess what you're doing is kind of like you've got an initial thing, then the deltas that come after that are a lot quicker, but that initial load, that initial data process is not
Yeah, so there've been case studies given, like HSBC gave one, it was on Google, but the same concept, and their overnight batch jobs were getting longer and longer to the point where they'd be clashing with each other.
Yeah.
But they managed to move them towards the serverless way of working, and they worked properly then.
Yeah. I'll come and grab you afterwards, because there's a feature that came to step functions last year called distributed map, and you can do massively parallel processing with step functions now. Like there's a use case on the blog about a customer doing high performance compute with Lambda and step functions completely serverlessly. So I can show you that after. Okay, cool. Cold starts. So cold starts are probably the most common thing that get talked about when we talk about Lambda, and this is that time it takes for your function to get ready to run, for the environment to be created, for the runtime to be set up, for your code to be downloaded. And historically, .NET and Java, for that matter, were two of the slowest runtimes. These compiled languages were considerably slower than Python, Node, and even Go. Now, there's a new feature that came to .NET, at least in .NET 7, called native ahead-of-time compilation. And what native AOT does is it compiles your .NET code to a native binary in a similar way to what Go does. So you've just got this native binary now that's ready to run on a given OS and processor architecture. So the numbers you can hopefully kind of make out on the screen there. That top screenshot is the benchmarks. That QR code, by the way, will take you to a repo we have for a whole range of benchmarks for .NET and Lambda.
On that screen it won't.
Yeah, well, not on that screen. Can we shift that left side? No, I can show you after this. Yes. On GitHub, we've got benchmarks for almost every runtime, so you can see how different configurations and different ways of running applications affect your runtime. But so typically with .NET 6, typically we would see about a 700 millisecond to 1.2 second code start. For Python, Node, that's 400, 500, 600 milliseconds. There's quite a difference there. For Go, which, as far as the managed runtimes go, is the fastest runtime, you're looking at a code start typically about 400 milliseconds for Go. With .NET 7 and native ahead-of-time compilation, we can get a code start time that matches Go exactly, or almost exactly. So we've got a P50 code start there with native AOT of 400 milliseconds and a max code start of 740 milliseconds. The Go comparison is 458 milliseconds at P50 and 563 milliseconds max code start. So both .NET with native AOT and Java are starting to move to these faster code starters, which make them more applicable for Lambda-based applications. But actually, and I love this stat whenever I talk about code starters. So when I was running them benchmarks, the way I ran the benchmarks was that I ran 100 requests a second for 10 minutes against Lambda. That equated to about 158,000 invokes of my Lambda function. 0.36% of them were cold starts. There's about 60 cold starts in that whole thing. And one of the developer advocates at AWS, one of the serverless DAs, he ran some analysis in Lambda, and this is on the AWS blog somewhere, and across the entirety of Lambda, 3% of all Lambda invokes are cold starts. So the reason I bring these numbers up is that if you're running an API on Lambda and you've got a relatively consistent load, you're likely to see relatively few cold starts. Yeah, it seems to be the most common thing that people talk about, right? Because as developers, that's all we see. Every time you deploy a new version of your Lambda function, you are guaranteed to see a cold start because you've changed things. So as you're developing, you're seeing this all the time and you're thinking, why is Lambda so slow? People say it's amazing. Once you get to production and you've got that consistent load, and remember, cold starts are only really relevant if you're doing user-facing stuff. If you've got a back-end job, a batch processing job, that's going to take 5 minutes to run, if it takes 700 milliseconds to start up, arguably it doesn't matter so much.
Can you do controlled releases of Lambda, so you can say release it, but it's only accessible to like these IPs or this percentage of users?
Yes.
Get around the cold start and deploy, could you?
So there's a couple of ways you can get around it. So the most common way you can get around it is a feature of Lambda called provision concurrency. So you can say to Lambda, I want 10 provision concurrency, and that will ensure at all times you've got 10 warm execution environments. With that, you then lose the ability to scale to 0. So you pay for that all the time, of course. And Lambda will still burst past that. So if you get 100 concurrent requests, Lambda will say, okay, the first 10 will be handled really quickly, but then you might get some burst beyond that.
Once it got to 8 of your 10, would it then be warming up? No, there's no sort of anticipated requirements.
So the downside to that, of course, is that you're paying for Lambda.
Yeah, but if you've got a critical system, you would pay for it, wouldn't you?
Yeah, absolutely.
No, I mean more.
Well, yeah. So the other way,
release sampling.
Yeah. So the other way you can do that is Lambda's got a feature called aliases and a feature called versions. So when you deploy a new version of your Lambda function, and this is what most people who are getting started with Lambda are familiar with, you'll always invoke the latest version of your Lambda function. You deploy some new code, you get the latest version. But with Lambda you can deploy a version, so you can say I want to deploy this new version of my code and also increment the version number. So then you have version 1 of your Lambda function and version 2. Okay, 3, 4, 5, 6, 7. And then you've also got Lambda aliases. So you can have an alias on your Lambda function. You might have an alias of production, an alias of staging, and an alias of development. And you can say I want this alias to point to this version.
Yeah.
Okay. So production's pointing to version 1. And then when you can deploy version 2, and version 2 will go live in Lambda, but your production alias is still pointing at version 1.
Yeah.
And then you can do your normal traffic shifting, 10% every 1 minute, blue-green deployments, canary deployments, any of that. You can do all that same things, then you slowly shift your production alias from version 1 to version 2. So you can do, depending which way you want to do it, you can do it both ways. The other thing to prevent cold starts that I see people doing quite a lot is setting up some kind of scheduled job to just ping your Lambda function every now and again, and that will work.
Just message with your statistics.
And eventually Lambda's just going to recycle them environments anyway. So you might think that you've got warm starts all the time, but actually you might just get one pinged off.
You're only going to get one warm environment anyway doing that, unless you do something.
Yeah, unless you do some funky things like
to
force it to cold start. Yeah. You could do one request every minute, and then in your application code put a sleep timer for 5 minutes, but then you get in.
Yeah, I suppose you could be invoking a function which makes 10 concurrent calls to your function to get those 10 environments running.
Yeah, but
or you could just use reserved currency.
Yeah.
The thing is with that, if your AWS themselves could optimize that part, and then all of a sudden your workaround is going to play hell with it.
I think the main risk is you just risk introducing issues for yourself.
If you're doing anything like that, you're going to have to handle that in your application code, which then makes your application code more complicated. Like I said, the best way, at least I've found, to deal with it is, as a developer, you're going to see it all the time, because every time you deploy a new version, you're going to get that cold start. Almost.
Just put it in your deployment pipeline to trigger the function as it's deployed, as soon as it's deployed, and then when you test it, it's already warm.
Yeah, well, yeah, I suppose so. But look at your production load, like get your function into production or against some kind of load test or a smoke test that's using actual real load that you expect against your system, and use that to form the basis of your is Lambda right for me with its cold start time, as opposed to using the experience of the developer. And of course, I'm not saying the developer experience is great, like you're getting a cold start every time, but just remember the fact that in production it might not be the same, because it's going to have different characteristics when it's running under a real load.
There's a use case thing as well, isn't there? How often do you really want low latency periodic calls?
Yeah.
You know, you're going to call it once every 10 minutes.
Yeah.
You wait for a bit. You're going to call it every 5 seconds. Hey.
Yeah, absolutely. Yeah. So there's a system before I started working at AWS. There was a system I worked on, and it had exactly that use case. So really low frequency of calls, but when it did get a call, it needed like double-digit millisecond latency. So what I actually ended up doing was running like a really thin API layer in a container that's always there, but really low memory, so it's always there, but it doesn't get using a lot.
I'll just go off and do a Lambda.
But yeah, exactly.
Here's your response.
Yeah, exactly. Here's your response, and then go off and do some other stuff, and then send the app. So request comes into your front end, that gets a really fast response to your caller. Lambda often does some work asynchronously, and then use WebSockets to send a message back to your front end that the work's been done. So there are ways around it if you have that exact use case. But yeah, like I said, if you're building, an application that's got a relatively steady state load, it's worth doing your own analysis on your own application use case as opposed to developer experience. Okay, so native ahead of time compilation, let's just talk about that a little bit, because there are some caveats with using native AOT that doesn't just make it, yay, 400 milliseconds cold start, let's just go and do native AOT tomorrow. Like, there are some interesting things. So we do have some pre-built samples. So if you're using the .NET new templates or AWS SAM, there are templates available that show you, like, give you like a getting started with native AOT on Lambda. And the functions look slightly different if you're using native AOT. So Lambda only supports long-term support releases of programming languages. And this is not .NET specific, this is across any runtime. If there's a so .NET 6 is available as a managed runtime, .NET 7 isn't, because .NET 7 is not an LTS release. Like I said before, Lambda does provide this functionality called a custom runtime, which is where you can bring your own runtime to Lambda.
Or someone else can bring the runtime.
Someone else can bring a runtime to Lambda, of course. And because native ahead of time compilation means that when you compile your application, you can run it without the .NET runtime, that means you can then use .NET 7 on Lambda using a custom runtime. So what actually changes when you're using a custom runtime, at least in this instance, is that all we need to do is just bootstrap the runtime manually. So what happens internally with Lambda when a new request comes in is that within Lambda there's what's called the runtime API, and that's just a HTTP API that you can make a request to, and it's something like localhost / invocation / next, I think the API endpoint is. So if you were going to bring your own runtime, you just periodically make a HTTP request to this HTTP endpoint. When there's an event available, you then get that. Okay? And that's what all of the managed runtimes are doing behind the scenes. It's just that we're doing that on your behalf as opposed to you needing to do that yourself. So with .NET 7 and native AOT, we have the tooling to be able to do that yourself. You don't need to do that HTTP polling yourself. We can do that for you. So what we're doing in that first orange box there is we're just bootstrapping the Lambda runtime. So we're defining our handler, and then we're just running the runtime. And what that .run async method is going to do is just set up that poller. It's just going to poll invocation / next for the next invoke that comes into that Lambda function. Okay? And we're just passing it the handler to use. And you see the function handler there is, relatively straightforward. It's just some business logic that's just going to two-upper a string that comes in. So that's the first thing you need to do if you're either bringing your own runtime to Lambda or you're using native AOT with .NET. You just need to bootstrap the runtime. The second thing that custom runtimes do with Lambda is that the way a custom runtime works is that Lambda will just look for a file called bootstrap. Regardless what runtime you're using, that could be a shell script, could be an actual executable, but Lambda's looking for a file called bootstrap. And if in your deployment package there's no file called bootstrap, Lambda will go, hey, I don't know what to do with that, and it'll just say error. So when you're using .NET, you need to ensure that the assembly, the compiled assembly that you generate, is called bootstrap. If you're bringing your own custom runtime, you might have a shell script that's called bootstrap.shell, and then that is what configures all this polling and all this invoke mechanism.
Could you just use a custom runtime to be your application and not have anything else, and use that as your way of patching? Would that get you faster cold starts as no additional code to be loaded unzipped?
Yes. I mean, if you could do everything you need to do in your application in a shell script, then...
Well, this could be anything, can't it? It's any kind of executable.
Yeah. The trade-off you get with cold start with custom runtimes is that initialization phase. You pay for the initialization phase in a custom runtime. So there is a slight trade-off, but yeah, you could do. Again, it's custom runtime. You can bring almost anything to Lambda if you want to.
I suppose that's part of why you pay for it, because you could be doing
absolutely
stuff.
anything. Yeah. Exactly. So that's the other thing. If you're bringing a custom runtime, you need a file called bootstrap in the deployable. With .NET specifically, one of the things you lose with .NET if you're using native ahead of time compilation use, so not with the custom runtime. This is a Microsoft .NET specific thing. You lose the ability to do a lot of reflection type programming, because what the native ahead of time compilation does is it's actually quite aggressive with how it trims your application, and it basically just trims out anything that's not being used. So if you're doing anything dynamic or anything with reflection, that code will potentially be trimmed out. Now, both the two biggest JSON serialization and deserialization libraries in .NET both very heavily use reflection. That's Newton Soft JSON and System Text JSON, which is the Microsoft built-in one. So what that means is that if you're doing serialization and deserialization in your application today, and you just try to take that straight to native AOT, it probably won't work because all this code is going to get trimmed out. So Microsoft introduced a feature in .NET 6 called source-generated serialization. And what source-generated serialization does is it generates the code needed to do serialization at compile time, not at runtime. And source-generated serialization could actually positively impact your application performance without native AOT, because you're not using reflection anymore. You're doing things with code that's already been generated at compile time. And the way you do that, I realize that's quite a small, blurry screenshot, but you create a new class in your project that inherits from the JSON serializer context base class. And that's a base class that comes from the System Text JSON namespace. So if you're using Newton Soft JSON today in .NET, you can't use source-generated serialization. You need to move to System Text JSON. And once you define this partial class, you just add attributes to that class to define the types that you want to be available for serialization and deserialization. So here we've got some custom objects to our application. We've got a product and a product wrapper object. And then we've also got the actual API gateway objects themselves, because the runtime is going to do that serialization and deserialization on our behalf, remember, so we need to specify them as well. So now we've got the custom JSON serializer context, and we can then tell Lambda to use our serialization context instead of using the built-in Newton Soft or System Text JSON serializer. And again, this may well have a performance benefit to your applications, regardless if you're using Lambda or serverless or containers, because this serialization code is now generated at compile time instead of runtime. What it actually does under the hood is just generate a whole load of static classes that have all the logic needed to do this. Okay, so what I was going to do now is show you AWS SAM and just how quickly you can get started. Is anybody using AWS SAM or the CDK today? Just out of curiosity.
Used it.
Okay. Let's see how we go. We always like risking a live demo. Oh, you've lost me up there, haven't you?
Shows how well you know it though, doesn't it?
One sec. GTK these displays. You're going to zoom in on me, you don't have to. Okay, cool. Let's just zoom that right in so everyone can see. So I've got the AWS SAM CLI installed now, and to get started I can just run the SAM init command, and SAM provides a whole bunch of templates to do a whole range of things, ranging from a simple hello world through to data processing and how to use step functions to do data processing. So there's a whole range of pre-built examples for how to use AWS SAM to build serverless applications. For the sake of this, I'm just going to use the hello world example. We definitely don't want to use Python. And these are all the runtimes that examples have been added for. So you can see everything from .NET to Go to Java through to Rust. Like, there's a whole range of different examples built into AWS SAM. I'm going to use .NET 6 in this instance. I want to package my code as a zip file. I don't want tracing on my function just for this example, and I'm going to call this CG 2023, for example. And this is going to go off now and just clone a template from GitHub, and it's going to create some files on my local file system using that CG-2023 name that I've just added. I always talk really, really slowly at this point because it does depend entirely on the speed of the internet. Okay, well that's cloning. Any questions? Yeah.
Can you, so for those single purpose functions you talk about permissions.
Mm-hmm.
I was curious, sort of by default, are there zero permissions, or is there some clever stuff that says, well, look, he's depending on DynamoDB clients, so we'll include. So you have to explicitly specify.
So the basic Lambda execution role has permissions to write to CloudWatch, which is logging, and I think that's just about it. So anything additional you want on top of that, and that's because, like I said, this idea of least privilege security, we're saying if you're using Lambda, you need to be really specific about what you want Lambda to do, otherwise it can't do anything.
That's pretty cool, actually.
Yeah, yeah.
And so if you deploy that thing, you just share it with the data, and you had included the permission, you get a sensible error back that says.
It'd just say, role blah 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 blah, role name blah 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 does not have permissions to call DynamoDB get item on table blah 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 blah. So yeah, the error you'll get back is the SDKs give you quite useful errors back. And like I said, so like for DynamoDB, for example, if you wanted to both query and write, there's probably 11 separate API endpoints for all the possible things you could do with Dynamo, right? So even like remembering which ones you need and which ones you don't can be, it's possible if you're doing not all things, but there's just a lot of IAM actions in AWS. So having that ability to go, I want DynamoDB read, and Sam will just handle the rest. It's quite helpful.
Just a separate question. Is there a limit on, obviously you have one function, but it could depend on like a gazillion services and so on that you define, and you code and you deploy. Is there a limit on that? You know what I mean? If you've got all these interfaces and services that you've injected as part of your own code, and it's like gigabytes worth of stuff, is there at some point does Lambda say no?
Yeah, so Lambda, when you deploy Lambda there's two ways you can deploy your code to like package your code for Lambda, if you will. The first is a zip file, and the max size of your zip, I will need to check because I can't remember.
500 megs.
I always get it mixed up if it's 500 meg zipped or unzipped. I think it's unzipped, but I'll need to check that. I'll have a look in a sec. If you use a container image, you can go up to 10 gig.
Yeah.
And there's a really interesting balance point where, so if you're doing like a really small Lambda function that's really, 10, 12, 15 meg, zip files are going to be faster than container images. And there becomes this inflection point where actually container images get faster at a certain size. And the reason for that is, the way Docker, a container image works in that it's just layers of different chunks, if you will. Lambda under the hood caches all these different chunks. So actually you can get faster once you get to a certain size to use container images as opposed to zip files. But in terms of what you do in your application code, that's only restricted by like you. If you wanted to load 1 million dependencies, as long as it sits within that size of your bundle, then you're fine.
It's like Rust's your fastest cold start.
Rust is insanely fast. I was doing some work. I put some stuff on YouTube at the weekend about Rust, and the cold starts are just silly how fast they are.
Come back next month. Hopefully.
Yeah, I can't. It's crazy.
Seen reports of 234 milliseconds with 1 gig of RAM.
No, so the lowest again. So for the benchmarks we've done for .NET that I had on screen, if you give a .NET function a gigabyte of memory, typically you're looking at about a 600, 700 millisecond cold start. Rust with 128 megabyte of memory, which is the lowest possible memory allocation you can give, is about a 200 millisecond cold start.
That's significantly faster
it's crazy. But then you've got to learn Rust, which has its own interesting.
It's a lot easier than writing in C, though.
It is a lot easier than writing C. I agree with that. Yeah, I actually quite like it now that I've got my head around the compiler and the intricacies of the language. It's actually a really, really cool language. But anyway, this is the .NET talk. I'll come back next week to talk about this. Yeah. Sidebar. Okay, so I've just run that SAM init command, and I've just opened this up in Visual Studio Code just to kind of give you an idea of what I get. You get a similar structure depending on what runtime you're using, and the folder structure you get will kind of align with what the idiomatic way of having your folder structure is in whatever runtime you're using. So we've got our Lambda function itself, we've got our function code here. Again, I'm not going to dive so much into the code itself. We've got a test project, so we've got some unit tests ready built, and we've also got a sample event payload, which I'll talk more about in a second. The key thing for AWS SAM is at the root of the folder that gets generated, I've got this file called template.yaml, and this is the actual template that's defining our resource. So you see we're saying we've got a global section here, and we can say I want all of the functions in this template to have a 10-second timeout and 128 megabytes of memory, and I can override that at a specific function level. So within this individual function I could say actually I want that function to have a gigabyte of memory, for example. Oh, I might still do. So what a weird default this is. It's saying 128 there and then 256 there. But anyway, yeah. So this is kind of how we can then start to define our resources. If you had, multiple Lambda functions, you could have 4, 5, 6, 7 defined in the same template. You could also put your databases, your queues, your event buses. You could put them all within this same template file. So what's going to happen now if I come back to my terminal and I'll run the sam build command, and what sam build is going to do is in essence do a for each over each resource I've defined in this file that's of type AWS serverless function. It's going to do a for each over all these functions. It's going to look at what the runtime is, and it's going to do something different based on what the runtime is. So if I've got the runtime defined as .NET 6, that's then going to actually go off, and if I go back to the logs, you can see it's actually compiled my .NET application. If this was like a Node function or a Python function, it'd just copy a file from one folder to another because it's interpreted, not compiled. So that's compiled my function now. It's done everything it needs to do to get that ready to run. And then I can just run sam deploy. And if I pass in this guided flag, this will take me through a little wizard now that I can define how this gets deployed to AWS. So let's call this CG. I don't know why CG. I was in Liverpool last week. Liverpool user group. That's Chester group. There we are. Naming things, it's hard. So this wizard will take me through a few different steps. So do I want to confirm the changes before I deploy? Let's live life on the edge. Do I want to allow Sam to create? So to your question about permissions, this is where Sam's saying, are you okay with me creating roles on your behalf? So if you've defined policies, obviously you want to say yes because you want Sam to set up them permissions. Let's not disable rollback. Again, we're living by the seat of our pants. One of the really cool features of SAM is that if you define a function in your template that has an API as its source, and you don't define authorization on that API, Sam's going to say to you, you've defined a resource without authorization, is that okay? And she's asking you to say yes, because this is now going to be a publicly available API. And then the last three questions are just, do I want to save that to a local config file? And I do. So the last three enters I hit then. Or just, do I want to save it to a config file? What's the name of the config file? And what's the environment to use for that config file? Hence why I just hit 3 enters. What Sam's going to do now is it's going to go off and upload, it's going to zip up my compiled application, it's going to upload that to Amazon S3, which is what happened there. And then it's actually going to go off and deploy that, and I'll actually get some real-time updates in my terminal window about exactly what's happening. So you can see the first set of things I got here is just telling me what's going to happen. So it's going to create Lambda, it's going to create the IAM role, it's going to create the function, it's going to create API gateway. And if you remember in my template, I've not actually mentioned API gateway at all here. I've just said I want a function that's sourced by an API. I've not configured API gateway at all. If you did want to add more advanced configuration to your API, you can simply say, REST API ID, and then you could actually define your API. If you need to add cores or authorization or any of that API stuff, you can do that. As a default, Sam will just create that for you on your behalf. And that's deployed. So after that's finished deploying, I'm just going to zoom out a little bit. Sam's then actually output the endpoint of my API, amongst other things. So if I hit that API endpoint now, and that is a cold start of a .NET Lambda function. And obviously this function is not doing anything, it's literally just like checking the IP address of the function, the environment it's running in, and returning a message. So it's not really doing anything, but
This is with 256 mega RAM.
256 mega RAM, yeah. So, is that a good youch or a bad youch?
Bad youch, it took forever, didn't it?
So the other thing I can do is I can run soundsync -watch, and I need to pass in a stack name, and I can't remember what I called that, so let's just go for that same thing again. And this is the feature of SAM where SAM's actually going to watch my local file system and redeploy things as I make changes. I'd advise not doing this in production because just don't. And this is going to go off, it does some initial bits of work to set up some resources. Let's just wait for that. Oh, it's creating from scratch, that's cool. Any other questions while that just sets itself up?
Did you use the, what was it, AOT?
No, that was just pure.
So your Lambdas don't get charged while they're not running, but I presume you get charged for storing. Yeah?
You get the, so if you're using zip files as the deployment mechanism, the zip files get stored in S3.
Yeah.
So you are then charged for this, whatever the storage cost of S3 is. S3 has a cost of data transfer in and out, but because everything we're doing is within the AWS backbone, then there's no charge for that data transfer. So it's literally just the storage cost of your code, which, again, if you've got gigabytes and gigabytes of application code, then that's obviously going to maybe have an effect. But your typical single purpose Lambda is 30, 40, 50, 60 meg if you've really slimmed down your dependencies.
That millisecond charge, is that just for while the handler's running?
Correct.
So if the environment hangs around for another few minutes,
yep,
that's on AWS.
So that example you just saw then where I actually hit the API endpoint,
yeah,
that was probably what, 600, 700 milliseconds maybe. I'll have probably been charged, well I won't have been charged because it'll be free because I'm in the free tier, but that'll have been about 5 milliseconds, 6 milliseconds. So if I just flick back to these numbers here, so you've got the cold start there on the left and the warm start there on the right.
yeah.
That cold start time is made up of the time it takes to set up the environment and the time it takes to execute the code. The warm start is the time it takes to execute the code. So although you're seeing like 1.6 seconds on the left, you're still only going to be charged for 6.41 milliseconds, right? So you only ever charged for the exact time it takes for your function to hit the handler and return a response.
Okay. And then the environment's sitting around unused for a couple of seconds until it gets another request. That's
Absolutely, yeah.
AWS is solving that.
Yeah.
That warm start time, so is that like the time between the request coming in and it hitting the handler function?
No, so that's Lambda, that's purely Lambda. So there'll be an extra bit of latency, which is API gateway talking to Lambda, Lambda talking back to API gateway. So that 6.4 milliseconds is...
That's the overhead of Lambda.
That's .NET on Lambda.
Yeah.
So the time it takes for API gateway to talk to Lambda and Lambda to talk back to API gateway is going to be the same regardless of the runtime you're using. The reason why we make these numbers, these benchmarks, only Lambda and not the integration time is because that integration time is the same whatever runtime you use.
And then if the actual handler function takes another 10 milliseconds, then it'd be 16.41 seconds. So that's not including the actual handler time itself. That's the time from the request hitting Lambda to it hitting the handler function, and then the response working its way back out.
That 6.4 millisecond is the exact time it takes for the function handler to execute.
But yeah, but surely that changes depending on how long your handler function takes to execute.
Oh, of course, yeah,
So
sorry,
that's
yeah,
like,
of course.
That's like for a no-op handler function. Is that right?
Yeah, if you were to put a 10-second sleep in your handler,
so
if you wanted
10
to,
seconds,
you'd be charged for 10 seconds, yeah.
Plus
Exactly.
the 6.41 milliseconds that's on that.
No.
Yeah.
That 6.4 milliseconds is the time it takes for the in the benchmarks. The benchmark application we've got is like a CRUD API against DynamoDB.
Right.
So that 6.41 milliseconds is the time it takes for that method.
Right, okay, so that's
In
actually including that DynamoDB
Correct.
project. Okay.
The call to Dynamo, the response from Dynamo is 6.4 milliseconds.
Right, okay.
So if I was to take that exact same code and put a 10-second sleep,
Yeah.
it'd be 10.641, So anyway, you know what I mean.
I know we're getting into specifics here now, but that's interesting. So if my DynamoDB was configured really badly, or was really slow, would I pay for that through the Lambda function?
Yeah.
Yeah, you pay for Lambda function and wait for your database.
Yeah, exactly.
Yeah, that's interesting.
Same would apply if you connect into like, you know, any SQL, anything like you're paying for the compute time of your application.
If you went with dedicated servers, you'd be paying for it as well, because you'd have to scale up the number of servers early because of the inefficiency of your database.
You'd use async, wouldn't you? So it wouldn't tie threads, you'd be processing other stuff at the same time.
Yeah.
Yeah, it's an interesting point.
No, it's just, it's interesting.
Yeah,
That's all it is.
Okay, so I've ran, if we just refresh a second, so I've run that samsync watch command somewhere up here, and then it recompiled my app again, and my terminal window's now sat here waiting for me to do something. If I come back into my application, and let's change my function, instead of returning hello world, let's say hello Chester, I hit save, that's going to go off and recompile my application. It's going to do that, and it's actually redeployed that already. So if I come back there, hit that again, code start, that's interesting. Fascinating. I love live demos, there it is. That's why it's a different endpoint. Okay, now we've got Hello Chester, and then we'll send Hello Chester on Wednesday. That's going to recompile, redeploy, update only the function that it needs to update. Hello Chester on Wednesday. So you can see that that's the cold start we see, and every time we make a change, we see that cold start.
Using this development flow would force you to not end up with an application that takes minutes to build, wouldn't it?
Yes, because Sam's smart enough to know I'm going to change this function, and then when Sam generates the zip file, which then uploads to S3, it hashes the zip file.
Yeah.
So actually, it's smart enough to know actually these 5 Lambda functions have got the same hash, so it's the same zip. I only need to update this one, and it will only update that one zip file, which is why it can have, if I had 4 Lambda functions and then I only changed that one, it would only then update the one Lambda function.
Yeah, so I've worked on like joint teams that have got Lambda-based applications that have got 10-minute deployment times, and it's just it's already too far gone to fix.
Yeah. Okay, so that was really quick. AWS SAM, like I said, there's lots of examples in here if you do want to get started for various different runtimes, if .NET's not your language of choice, but AWS SAM is a really good way of getting started that is production ready, if you will. It's not like right click deploy from your IDE. You could define your entire application resource in SAM, deploy that using CI/CD. So that was.
So would you run SAM in your CI/CD, or would you run what SAM generated?
So typically, SAM's got the 2 commands. It's got SAM build, which will generate all your artifacts, and SAM deploy, which likes to deploy things. Typically, step 1 of your CI/CD will be unit test, SAM build. Then you've got that artifact, and you take that same artifact, SAM deploy, SAM deploy, SAM deploy. And when you run SAM deploy, you can pass in like parameters. So you could say SAM deploy parameter override environment dev, for example, and that would then deploy it specifically for dev, probably specifically for whatever environment that you want. But yeah, same flow that you would have if using containers, you generate your container up front and then deploy that same container to all different environments. 2 really important bits on there, just before I shut up, for finally honest, is my email address and my Twitter. If there's anything at all that comes up, .NET or serverless or otherwise about AWS, please feel free to reach out on any of the 2 platforms, and I'll be happy to answer any questions that come after tonight. If there's more questions tonight, then fire away.
So
Do the execution environments have any sort of local fast storage?
Yes, so you get on, I think it's /TMP/temp, you do get some ephemeral storage. The ephemeral storage is specific to that environment.
Yeah.
So if you obviously got 2 invokes come in, you couldn't guarantee you'd have the same file storage. Kind of the point before about execution environments can mess with things a little bit, because you might store something there and then forget to clean it up, and then your next request comes in and it's already there. And you can also attach file systems to Lambda functions.
Yeah, so if I've got, we have APIs that need resource files.
Okay, yeah.
So having them reused between multiple requests is a good thing. We are used to deploying that to local physical servers at the moment. We're
Yeah.
moving away from those, but we are used to then having PCI attached SSD type latency, which has always been a pain point when we're trying to move things to cloud.
Yeah.
Going from kind of less than single figure millisecond latency to
So there, up to I knew this had changed, you see, so I just thought I'd Google it, but up to 10 gig. It used to be 512 megabyte of ephemeral storage, you can now up to 10 gig of ephemeral storage, and that's on the /temp directory, if you will. Obviously, if you were to bundle your resource files in within your zip file, that would then feed into the size of your zip file, not to your temp directory. The temp directory is more intended, you've got something happening in your application, you need to write it and then read it again, something like that. Again, so back to the question about zip files. 50 meg is the max zipped size of your 250 unzipped, 250 meg unzipped. So if it's any more than that, you need to look at container images.
Or you need to question your choices.
Well, yeah, or slim down your dependencies. Yeah, I guess so.
Any other questions? I've asked online, but nobody's got any questions online.
Have you got any slides on authorization access controls? That's some side of Amazon that I don't really.
Like identity and access management.
Yeah.
No. There's actually a really, really awesome reInvent talk. So reInvent is the annual developer conference. This one here. So it's a couple of years old now. reInvent 2018. But Bridget Johnson is now I think she's the director of IAM. But this talk is awesome for understanding IAM in more details and how IAM policies work. So if you're not familiar with AWS, IAM is basically the AWS service that controls access to every other AWS service. It's within IAM that you define what certain users or roles are allowed and not allowed to do. And at a high level, the rule is if it's not in an IAM policy, it's a deny. If you've got an explicit deny, that overrides everything. Otherwise, you've got an allow, but you've got to be explicit about your allow. But you can combine things in really interesting ways. This talk is awesome. It goes from the simplest IAM policy right through to doing complex role-based access control, and based on the tags that a role have got, give that access to specific resources. So yeah, Bridget's awesome. I don't have any to hand on IAM. I use the SAM policy template, as you see there.
Cool. Final question: are you the only James in the UK from Amazon?
I was really surprised actually. So I've been at AWS for about this is reInvent last year, so you might want to just grab a photo of this one as well, because it's a bit more recent. So yeah, I've been at AWS since September 2021, and when I joined, I got to pick what my username was. So I thought you get suggested some which are like JEAS125, whatever nonsense. But you could also try your own. I was like, let's give this a try, see what happens. And nobody at Amazon seemed to help James UK. So I can't ever move to Canada, but
that's true.
Although I don't think I'll ever lose this accent, so I'm always probably quite clearly James UK. Yeah.
Great stuff. Thank you very much.